Hello, this is Pat Hindle, editor at Microwave Journal. It's my pleasure to welcome you to today's webinar on Introduction to Magneto-Dielectric Materials for Antenna Miniaturization, presented by Carl Sprentel, Business Development Manager at Rogers Corporation's Advanced Connectivity Solutions. Before we begin the presentation, let me cover a few items about the On24 webinar platform. In the center of the screen, you will see a window containing the presentation. You may enlarge this to full screen to get a better view of the slides. The window on your screen labeled Resource List contains a copy of the presentation, which you can download at any time. This webinar is being recorded and will be available for replay within about an hour from when we conclude, allowing you to watch it again and recommend it to colleagues who weren't able to join us for the live event. You will find a link to the recording in the events section of the Microwave Journal website. If you're having technical problems, please click on the yellow box with the question mark at the bottom of your screen. It will take you to a helpful user's guide. After the presentation, we will have time for questions. So if you'd like to ask a question, just type it into the Q&A box on your screen at any time. Magneto-Dielectric Materials are a newly available class of controlled impedance materials for use in UHF and VHF antennas. They possess controlled permittivity and permeability, both greater than 1, allowing for the materials with a high refractive index to be produced. Numerous publications and measurements also support the ability of these materials to miniaturize certain antennas with minimal impact on bandwidth, achieving designs closer to the fundamental limit of electrically small antennas. The addition of the permeability to the subset of laminate properties also allows for new antenna constructions and design techniques to be leveraged. However, unlike linear dielectric materials, magneto-dielectric materials exhibit a strong frequency-dependent loss tangent and intrinsic impedance. This drives an increased importance on the characterization and modeling of these materials. This webinar will address the basics of the magneto-dielectric materials and different considerations which should be understood when designing a miniaturized antenna utilizing these materials. At this point, I will introduce today's presenter. Carl Sprentel joined Rogers Corporation in 2010 and currently holds the title of Business Development Manager for Rogers Corporation's Advanced Connectivity Solutions. Previously, he held various titles including Applications Engineer, R&D Engineer, and Principal R&D Engineer. He has worked in a variety of areas for Rogers, including technical marketing, emergent opportunity assessment, development for circuit architectures, and development of magneto-dielectric and other novel electronic materials. He has 13 years of experience in product and technology development and holds a bachelor's and master's degree in electrical engineering from Arizona State University. So at this point, I will turn the presentation over to Carl.
Thanks, Pat. So today we're going to do a brief introduction to magneto-dielectric materials and how you would leverage these materials into miniaturizing an antenna. What we'll cover today is first, what is a magneto-dielectric material? Then understanding how the properties of these materials will depend on frequency, and then why you would want to use these materials in an antenna. From there, we'll talk about measurement and characterization of magneto-dielectric materials, which is a necessity to be able to effectively model these materials in something like a 3D electromagnetic simulator. And finally, we'll do a brief introduction to beginning an antenna design with these materials. First, starting out with use cases or how you would use these materials, and then go through some examples of the design of a patch antenna leveraging a magneto-dielectric material. So at a first level, a magneto-dielectric material, they are a composite or a ceramic material that have both permeability and permittivity greater than 1. They are not a metamaterial where you would, say, create a circuit structure on a copper-clad laminate that gives you a permeability or permittivity greater than 1 over some narrow frequency range. The intrinsic material properties are what drive the high permeability and high permittivity. Basically, what you're doing when you're adding a permeability to a material is you're increasing the intrinsic impedance of the composite or of the material itself and increasing the refractive index. So it allows you to get a material that produces a smaller antenna and at an impedance that allows you to maybe maintain more of the bandwidth of the antenna as you shrink it. The use of a magnetic material in antennas is not really a new concept. If you go back and look at, AM radio antennas dating back to the 1930s, or more recently RFID or near-field communication antennas, all of these structures have often used a ferrite material or other magnetically permeable material to either miniaturize the antenna or allow a small antenna to be placed closer to a ground plane. The common theme with these designs, though, is that you're operating in a frequency range maybe below 20 megahertz, and generally you're looking at a not very efficient antenna. So in the case of something like a radio antenna made with ferrite, you may use the antenna as a receiver, but not as a transmitter, just because the antenna is not particularly efficient. There has been a drive over probably about the last 20 years where researchers have worked on development of magnetodielectric materials at increasingly high frequency ranges. And to kind of summarize the approach that researchers have taken very quickly, it's generally one of a couple paths. You either use a magnetic ceramic, so a ferrite material that's engineered to operate at a higher frequency. You make a composite structure by putting a ferromagnetic metal into a polymer, or you make a composite structure by putting a ferrite ceramic into a polymer. And these all have different advantages and disadvantages. A composite with a ferromagnetic metal, you can generally get a permeability that remains out into a higher frequency range, with the trade-off that you get a higher magnetic loss, a higher dielectric loss because you're putting a conductive material in an insulative medium, and a permittivity that's generally much larger than your permeability. The other approach in the composite structure is to take a ferrite ceramic powder, put that into a polymer matrix. Generally, this will give you a lower permeability than a metal product at the same volume fraction of filler, but with a much lower dielectric loss, a much lower magnetic loss, and a permeability that can be closer to permittivity, but generally your permittivity is still slightly higher than permeability. The third approach is a ferrite substrate. So you make a ceramic material and you can metallize it to produce a magnetodielectric material. This gives you a higher permeability at a higher magnetic loss generally, with also a higher dielectric loss, and a mu that's approximately equal to epsilon, and the size is generally limited to the size that you can sinter a ceramic tile into. But after all these years of research, there are now materials available that have useful magnetodielectric properties into the range of a few hundred megahertz, say 500 megahertz. But they still exhibit a frequency-dependent permeability, and so you need to take that into account. To go into a little bit more detail on the frequency dependency of permeability, if you're used to using a low-loss dielectric material, you can say that from 1 gigahertz to 100 gigahertz, maybe you see a few % change in dielectric constant, and dielectric constant decreases by a few %, and dielectric loss may increase by a few %. With a magnetic material, it doesn't have that simple of a relationship. Fundamentally, these materials will have a frequency-dependent permeability and magnetic loss. And they'll all have a curve that resembles the one shown on the screen here. Basically, at a low frequency or up to a first critical frequency, which we'll arbitrarily call F1, the permeability will be flat, and the imaginary portion of permeability will be low, meaning that you have a low-loss material. Above F1, the real portion of permeability will begin to rise. The imaginary portion of permeability will begin to rise very rapidly, and you're now making a material that is higher in loss. The material will behave with a higher loss in this frequency range. At a critical frequency called FT, that is the cutoff frequency of the material. And what that basically means is it's the peak of imaginary permeability. So your magnetic loss has now gotten as high as it's going to be. And above that frequency, it will actually decline. And there's been a lot of research in this field actually dating back to Phillips in the 1930s and a researcher there named Snoke. And he developed what's called Snoke's law for ferrite materials or magnetic materials. And it basically says that if I take my initial permeability and my cutoff frequency for any family of materials and multiply them together, that product will be constant. Or another way of saying that is, if I want to go higher in operating frequency, with a higher cutoff frequency, I will trade off the permeability of the material. So I go to a higher operating frequency, I need to go to a lower initial permeability. And the research in the field has really been developing materials with higher Snoke products or a higher product of initial permeability and cutoff frequency, and then figuring out how to engineer the cutoff frequency of the material so that you get an acceptably large low loss region for use in an antenna. All right, so we understand that there's some limitations to the materials primarily in terms of frequency, and so why would you want to use these materials to miniaturize an antenna? At the most basic level, if you have an electromagnetic wave propagating through a medium, the medium will slow down that electromagnetic wave. And the rate at which it slows it down is the square root of permeability times permittivity. And so we'll call that term, which is mu eps, the square root of mu eps, the refractive index of the material. So if you get a high product of mu and epsilon, you're reducing the wavelength of that electromagnetic wave in the material by that high product. At the same time, a material will have an intrinsic impedance, or the ratio of current to voltage. And that intrinsic impedance is a function of permeability and permittivity as well, but it's now a function of the ratio rather than the product. So if I make a material that has a very high permittivity, and that will give me a very high refractive index. At the same time, it will give me a low intrinsic impedance, which means that if I've got a wave propagating between two medium, that impedance discontinuity will lead to reflectance at the interface, or reflection at the interface. Now, if you make mu and epsilon equal to one another, that term will cancel out. You now have a material that has a high refractive index, the product of mu and epsilon, but in a substrate intrinsic impedance which is matched to the impedance of free space. So that basically you don't have an impedance discontinuity between these two medium. The impact of that on antennas is going to vary widely by the type of the antenna that you design using these materials. But a common antenna that's built utilizing copper-clad laminates would be the patch antenna. And in 2000, R.C. Hansen and Mary Burke published a paper in Microwave and Optical Technology Letters where they derived the fundamental relationship between permeability and permittivity and bandwidth for a patch antenna. And if you've read a paper on magneto-dielectric materials since 2000, you've probably seen this formula before. I think this is probably the most widely cited paper in the use of magneto-dielectric materials for antenna miniaturization. But the real point of this is when you miniaturize an antenna using a magneto-dielectric material, and let's take an example of I've got a dielectric constant of 36 material, and I've got a mu equals 6 and epsilon equals 6 material, and I build a patch antenna on both of those substrates. I'll get the same size antenna using both of those substrates. The difference is the one that's built on the magneto-dielectric material, you would expect to have about 6 times higher bandwidth than the one that's built on the dielectric material. Now, so the way you'll use these materials is a little bit different than maybe a conventional PCB material, where you're just simply going to etch a circuit pattern on the top. And that's a result of the properties of the material. So the frequencies that these materials are used are typically in lower frequency ranges, which is also fortunate in that the antennas are also larger at these frequency ranges, so there's a greater demand for antenna miniaturization. The electrical performance, as we've already mentioned, is a strong function of frequency. And the other point is low loss for a magneto-dielectric material is going to be higher than a low-loss dielectric material. And so a key component of antenna design is understanding the losses of the material and then designing your antenna in such a way that you're able to maintain your efficiency targets with the losses of the material taken into account. There has been some research that's postulated that the relationship between loss tangent and efficiency is not the same between a magneto-dielectric material and a dielectric material. So it's not it's not exactly the same impact of loss, but you still need to take the loss into account when you're doing a design with these materials. And so understanding the frequency properties of the material and understanding that you need to have a good model of this material to do your design, we'll talk now about the measurement and characterization of magnetodielectric materials. Now, this is also going to be a little bit different than a dielectric material. So we typically characterize circuit materials by one of a number of resonant test methods, which give you dielectric constant and dielectric loss at a single frequency point, right? So it could be something like a long strip line, split post dielectric resonator, a full sheet resonator, or a clamp strip line resonator. And these will give you, your dielectric constants at one frequency point, or in the case of the long strip line, at multiple frequency points. But if you use that same method to characterize a magnetodielectric material, what it'll give you is the product of mu times epsilon, which is an interesting piece of information to have, but it's not a sufficient information to perform a design. So then we look at non-resonant measurement methods. And if you look at what we typically do for PCB materials, it's things like microstrip insertion loss or differential phase length. And those will give you more information about the magnetodielectric material, but it will also include the effect of a conductor. So we're looking for a way to characterize the intrinsic properties of the material. And what we found and recently published a paper on is that the best way to do it is a combination of a coaxial airline method. So you measure the puck of the material in an air coax cable. And then you use what's called a Nicholson Ross weir extraction to take scattering parameters and transform them into real and imaginary permeability and real and imaginary permittivity. Now that structure, if you look at it, you get your permeability, your measurement, because your H field is circling the conductor, you get your permeability measurement in plane, and because your electric field is working radially out from the center conductor to the outer conductor, you also get your permittivity measurements in plane. There's a second point about this measurement in that your permittivity measurement will be very sensitive to sample size, because if I introduce any sort of an air gap between these two conductors, where in the region where I'm characterizing my sample, that air gap will make a big difference on my effective permittivity. Your permeability measurement is a little bit less sensitive. So the airline will give you in-plane measurements for both permittivity and permeability, with a pretty accurate and precise measurement for permeability and a slightly less accurate and precise measurement for permittivity. So we found that combining the airline measurement with a second resonant measurement will give you the best characteristics for both. The second point is that the magnetic your permeability measurements, you generally care about the in-plane value. But if you're making a microstrip circuit using these materials, you also need the through-plane value of permittivity and dielectric loss. So we added in a full sheet resonant method that gives you now your permeability in plane and your permittivity through plane. And then I can use that to extract my z-axis permeability or permittivity for the material. So this is an example of the output of the Nicholson Ross weir extraction for a material called Magneto-Dielectric 555. So you'll see that your permittivity is relatively flat within the measurement air of the instrument, and that it stays flat over a range from 100 megahertz to 5 gigahertz, and this is on a log scale on the x-axis. At the same time, you'll see your permeability measurement will match roughly with the curve that we showed earlier, where you've got a relatively flat permeability at low frequency, then a knee in your permeability curve above which your permeability value will rise and then begin to decline. But because my permittivity number is flat, I can now just use a single value for permittivity across that frequency range. So to accurately model a microstrip circuit, what you'll do is take the full sheet resonance value, divide out your x value for your xy permeability, and that'll give you your z-axis permittivity. And now I've got a z-axis permittivity and an xy permeability that I can use to model a circuit. This is some examples of correlation between modeling and measurement. We modeled these circuits in Sonnet software, and we then measured them in the lab. And you'll see that there's a reasonably good correlation between modeling and measurement, and the correlation improves as the circuit gets thicker. At the same time, we also looked at the insertion loss of the material, and you'll see again, within the low frequency range where the material is well behaved, the models and measurements correlate very well. And then in the higher frequency range where the loss is changing rapidly, the model and measurements will still correlate reasonably well, but begin to diverge a little bit. So another way you can think about these materials, if you're just used to thinking about dielectric constant in your circuit design, is simplify this to two different dielectric constants. One is the dielectric constant that will give you the same wavelength reduction or the same refractive index, and that's what we'll call the miniaturization equivalent. And then the second is a equivalent dielectric constant for the impedance of the material, which we'll call the impedance equivalent. Now, your impedance equivalent dielectric constant is of course, the ratio, the square root of the ratio of mu to epsilon. And for this example material here, we see that the impedance equivalent is approximately 1, while if I take my in-plane values to calculate my miniaturization equivalent, I get something a little bit above 36, around 38. So you've got the miniaturization factor of a high dielectric constant ceramic with the intrinsic impedance basically of air. Now, when we begin to talk about using these materials in an antenna design, we can start talking about different use cases for the materials. So let's take an example. I've got a Magneto-Dielectric material that has a relative permeability of 6 and a relative permittivity of 6. My first point is now my impedance is approximately matched to free space, which means that there's little to no reflection for a wave traveling between the material and air. I've got a very high refractive index, or roughly equivalent to a material that has a dielectric constant of 36, which is great if you want to make a very electrically small antenna. But then you have to take into account your design considerations, right? For antenna size, do you want to make the antenna as small as possible, or do you want to make it just small enough? And if you're looking at making something just small enough, and you've got a fixed refractive index in the material, and only one value available, you'll need to start thinking about some other ways to control the antenna size. When you start thinking about other methods of controlling antenna size, you then need to think about what's the dimension of the antenna that I'm looking to reduce. Is it XY? Is it XY and Z? Is it Z only? And then you need to think about what trade-offs you're willing to make in a design. Are you looking to make an antenna that has a very high efficiency, or are you willing to trade efficiency for size or efficiency for bandwidth? And then understanding, the radiation pattern and gain that you're trying to achieve in the antenna. Now, when you start looking at this, you can begin to leverage some additional degrees of control with Magneto-Dielectric materials that may have been more difficult to leverage in a dielectric-only material. First degree of control is how you use the material, and we'll talk about 3 different kind of basic types of use case for the material. Second is now because I have a very high refractive index, I can partially load the antenna with this material and take advantage of some miniaturization, but not take advantage of all of the miniaturization that the material offers. And then the third is, do I want to add in some additional conventional dielectric materials into my design? So starting on use cases, at the most basic level, if you're looking to reduce the height of the antenna, and this is an overly simplified drawing of a dipole antenna as an example. But let's say I've got a dipole antenna that's going to be placed above a ground plane. I want to place that dipole antenna about a quarter of a wavelength above the ground plane so that my interaction with the ground plane is constructive interference rather than destructive interference. And in a case of an antenna that's operating in the VHF or UHF range, that distance, that quarter wavelength physical distance or electrical distance can translate to quite a large physical distance. So one basic use case of a Magneto-Dielectric material is simply to allow you to put an antenna closer to a ground plane, right? And so I use the Magneto-Dielectric material as an electrical spacer to give me a longer electrical distance and a shorter physical distance. A second use case would be I want to control how much miniaturization I get from the material. And one way to do that, and particularly for something like a patch antenna, is to use a combination of dielectric and magnetodielectric material in your laminate. So let's say I've got a patch antenna. My electric field is going to be in the Z direction dominantly. My magnetic field is in the XY direction. So if I put a low dielectric constant material between my radiating structure and my ground structure, that low dielectric constant material will reduce the effective dielectric constant seen by that patch antenna fairly quickly, or a small amount of material will have a large reduction in the effective dielectric constant of that substrate. My magnetic material will be based on, the reduction in permeability will be based on relative volume fractions, or basically a series mix for electric properties and a parallel mix for magnetic properties. So I can control my miniaturization factor, the product of mu and epsilon, by reducing my dielectric constant and still maintaining most of my permeability, which, if you go back to the patch antenna example, is the best way to effectively increase or maintain the bandwidth of a patch antenna, is to get your miniaturization from permeability. The last use case is I want to make my antenna very electrically small, and so you can use the material as a standard copper-clad laminate. And what we're showing on the screen here is a 300 megahertz patch antenna, and it's been reduced from maybe a natural size of about 17.5 inches down to a size of about 4 inches and a 6-inch ground plane. So you're making an antenna that's extremely electrically small. Now, of course, the caution is the classic relationship between antenna size and antenna performance will still apply. So there are some trade-offs that occur when you make an antenna very small, and it becomes sensitive to magnetic loss. It has maybe a narrower bandwidth than some of these other use cases, and then you need to take into account the performance of the resonance structure over temperature. Nonetheless, it's still a good way to make an antenna very small. So if you do a kind of a qualitative comparison between these methods, if you're looking for miniaturization in one axis or a smaller degree of antenna miniaturization, and you want to maintain the most efficiency and bandwidth possible, the use case that kind of is a good starting point is the cavity loading element. At the other extreme, if you're trying to make the antenna as small as possible, the use case that you want to look at is the laminate. And then if you're looking for some trade-off in between the two, you're looking at something like a hybrid use case where you're putting a PCB material with a magnetodielectric material and building a stack up. Now, if you were to compare this to a control material, which would be a high dielectric constant ceramic, the high dielectric constant ceramic it's possible to get a very low loss in these ceramic materials. So the efficiency between the dielectric ceramic and the magnetodielectric use case, laminate use case, you'll see a higher efficiency potentially with the dielectric ceramic. See the same miniaturization factor between the two, but the laminate and all of the other magnetodielectric use cases really enable you to achieve that miniaturization while maintaining more of your antenna's bandwidth. Now, here's a quick example of a cavity loading use case demonstrator. And what we're doing is on the left-hand side of the screen, we're looking at the return loss of the antenna. And on the right-hand side of the screen, we're looking at an increasing volume fraction of magnetic material. And what you'll see is as you're adding more and more magnetic material to that stack up, the resonant frequency, or the frequency at which your antenna will accept energy, is moving lower and lower in frequency. And the antenna's becoming more, effectively miniaturized, right? I'm taking an antenna that maybe naturally would work at 500 megahertz and making it work at down to 220 megahertz. And you also see that even though your structure of the height is quite small, you're able to achieve an antenna with a very wide operating bandwidth, something in the 200 to 400 megahertz range. And this is a dipole antenna that's placed above a ground plane. Now, the second point is if I were taking that dipole antenna and I'm just loading in a bunch of absorber material to it, I could see a similar effect. right? You can introduce bandwidth to an antenna by making it more radiative or by making it lossier. And so what we do at the end is we take basically a cap structure, place it over the outside of the antenna, and suppress the radiation. Now, if my antenna were becoming wider in bandwidth due to additional loss, when I suppress the antenna's ability to radiate, I wouldn't see much change in bandwidth. Because the bandwidth in this case is actually coming from antenna radiation, when I suppress the radiation of the antenna, my bandwidth reduces. And it's kind of just a basic way to show that the bandwidth enhancement that I'm getting in this antenna is not a function of loss, but rather of the intrinsic properties of the material. So now we'll dig into kind of a basic design example with a patch antenna. And what we're looking to do here is reduce the volume of a 300 megahertz patch antenna by a factor of 4. So we're not looking to make this as small as possible. We're looking to reduce the volume and maybe make it smaller than it naturally would be. At the same time, we want to look at how do we minimize the weight of the antenna and how do we maximize the bandwidth and efficiency of the antenna. And so as an example, what we're doing here is we're partially loading a linear polarized patch with a Magneto-Dielectric material, and then we're going to evaluate some different shapes of Magneto-Dielectric material to see how they impact the bandwidth, efficiency, radiation pattern, and gain. Now, this work was done by a customer's collaborator of ours called TQ Antennas. And so we're starting off with a air-loaded 300 megahertz patch antenna, and this is our control, right? So you see the patch dimensions, the ground plane dimensions, the height of the antenna. You have a 4% fractional bandwidth and a center frequency of roughly 300 megahertz. When I look at the radiation patterns of the antenna, I'll see a realized gain of about 8.7 dBi, which is typical for an air-loaded patch. These are my horizontal and vertical beam widths. And then because I've got a low-frequency patch antenna that's loaded with air, my efficiency can be quite good, and we get an efficiency here of 98%. Then we looked at the field distributions on that patch antenna. So to try to understand where to place the magnetic material, you want to look at where the magnetic field is strong. And what you see in this lower part of the screen here, the magnetic field is strongest along the non-radiating edges of the patch antenna and near the feed and then through the center of the patch. So looking at those structures, we can kind of think, oh, what are some potential shapes that we could use to load the magnetic field of the antenna, or load the region of the antenna where the magnetic field is strongest. And we'll look at quite a few different examples here on the next few slides. So this is the first set of shapes that we evaluated. You've got a rectangular structure where you just put a block of material in the center of the antenna, a hollow rectangular structure where you're going around the edges of the antenna, a solid cylinder structure on the antenna, and then a hollow cylindrical structure on the antenna. And then kind of trying to directly follow the shape of the magnetic field, there's a bow tie structure, and we also look at the bow tie structure in the opposite direction. A couple more shapes here, so blocks of Magneto-Dielectric material along the radiating edges, blocks of Magneto-Dielectric material along the non-radiating edges, and then this H shape, which is a simpler version of that bow tie structure. So if you look at the radiation patterns of these different shapes, you'll see that the placement of the magnetic material will influence the shape of the antenna's radiation pattern. So generally, you're skewing the radiation pattern in the direction of where the magnetic material is placed. So the hollow rectangular shape, you get something that looks similar to the original patch. The hollow cylindrical shape, you're skewing the radiation pattern maybe a little bit off bore site. And then the cylindrical shape, you're getting a lower gain over a very wide angle. The bow tie shape along the x-axis, you're actually widening your antenna pattern along the x-axis, and similarly with the bow tie pattern along the y-axis. Looking at the blocks, you'll see that these all have about the same radiation patterns, with the exception of the H-shaped block along the non-radiating edge, where I'm now widening out my pattern again. So if I look at kind of comparing the performance of these different antennas, and this is quite a large list, so we'll just hit the high points here. If I look at my air-loaded patch antenna, that does give me the best efficiency. It's the largest antenna, and it's the best efficiency. If I'm looking at the different shapes, and my figure of merit is fractional bandwidth times efficiency divided by antenna volume, that bow tie along the x-axis represents the best performance. So I've actually, in this bow tie example, I've increased my bandwidth from my starting point. I've maintained most of my efficiency, and I've been able to get a figure of merit that's normalized to about 6 times that of the air-loaded patch. If I look at the rest of them, you'll notice that in all cases, I've been able to about maintain or even increase the bandwidth from the original air-loaded patch antenna. But in some cases, I've made a fairly substantial trade-off in antenna efficiency. So that kind of concludes our introduction to magnetodielectric material. These are materials that are now becoming commercially available for frequency ranges into the few hundred megahertz range. You really can think about them as fundamentally another degree of freedom in the design of an electrically small antenna. And to effectively design with these, you need a good starting model for the material. And that model needs to include frequency dependency, permeability, and loss, and an understanding of the anisotropy of the material. A matched mu epsilon material starts to open up different use cases that can be leveraged in designing an antenna beyond that of a copper-clad laminate. You can look at structures like a cavity loading element or a hybrid structure that really were maybe less attractive with an all-dielectric material. And through careful design of an antenna utilizing these materials, you can get antenna miniaturization with performance improvements, right? So you can look at ways to enhance the bandwidth of your antenna, minimize the weight that's added by the magnetodielectric material, and carefully minimize the impact of material losses over that frequency range. And so at this point, I will open it up to questions and take any questions at this time.
Great. Thank you very much, Carl. Excellent presentation. These are a really interesting class of materials. So we have a few questions, but if you want to ask a question, just enter it into the Q&A box, and we'll get to as many as we can. First question, ferrite is normally gyrotropic, and dielectrics are anisotropic in substrates. How do you account for these effects, especially for ferrite containing magnetodielectrics?
The key that we've found is generally to characterize them in multiple axes. So looking at both the combination of an airline measurement and a resonant measurement method. The gyrotropic nature of the materials, we are currently evaluating methods of characterizing these materials under bias fields. But generally, when you're putting these materials into a composite structure, you're reducing the impact of some other changes because you're averaging the magnetic material or the ferrite's properties with the properties of a polymer system.
Okay, great. Next question. Can we have a electrically small, like 2 centimeter maximum at the frequency of, let's say, 300 megahertz, which is lambda over 50, and is referring to slide 15, which I'll push here?
It may be possible to do something like that. I mean, you're starting with if you do a patch antenna, you're starting with basically a half wavelength, and then you reduce that half wavelength by the effect of the magnetodielectric material. Going to another structure, like a PFI antenna, may allow you to make it even smaller. When you're going to an effective size that's something like a lambda by 50, you're going to be making a lot of trade-offs in the antenna's performance. So if you're okay with a narrow bandwidth and a narrower bandwidth than you would see in this larger patch example, and maybe a lower efficiency, it may be possible. We haven't evaluated anything that's that electrically small.
Okay, next question. How much miniaturization can be expected from magnetic part of the material?
So square root of 6 is coming from the magnetic part of the material. Square root of 6 is coming from the dielectric part of the material. Now, obviously, if you're making like a microstrip structure, that's affected by the fact that your fields are contained both in the material and in air. So you'll get less than that factor of 6 reduction.
Okay, next question. Can you make some comments about the MPA dominant first mode TM01 with ME substrate in comparison to non-ME cases? Any changes in the radiation pattern?
I think I will pass on that one. I can follow up offline. That is something I probably want to bring in one of our PhDs to answer.
Okay, no problem. Do you have frequency independent materials with a low tangent or loss tangent? For example, for 2 gigahertz with a permittivity and magnetic permeability are equal to 2, or for 1.5 gigahertz are equal to 1.5, etc.
We're looking at that. The trade-off is generally correct, right? So if we're going up in operating frequency, we will be going down in permeability. The real tricky part comes in that the dielectric constant is coming from a mix of the ceramic properties and the polymer matrix properties. And the lowest dielectric constant polymer that's out there is something like 2.1. So your permittivity is always going to be something higher than 2. And the tricky part becomes trying to get the permeability to be high enough at those higher frequencies. So we don't have any materials at those frequencies available today, but that's generally the direction that our research has been heading, is increasing the operating frequencies of these materials.
Okay, next question. Can you elaborate on the anisotropic nature of the materials?
Sure. So what you have is a platelet, a ferrite platelet that's non-spherical, that's going into a polymer matrix, and it tends to orient as you're going through any sort of process step. So you have a higher permeability in the material in plane. And now because your dielectric constant is a result of a mix between polymer and ceramic, and the ceramic has a dielectric constant that's much higher than the polymer, you end up with a dielectric constant which is higher in plane as well. The z-axis, what we find is, for something like this mu equals 6, epsilon equals 6 material, where you have a permittivity of about 6.5 in the xy direction, permeability of about 6 in the xy direction, and permittivity in the z direction of about 5. So it's a lower permittivity in the z-axis than it is in the xy axis.
Next question, can you discuss any differences in drilling and plating of this material compared to typical PCB laminates?
So it'll behave, in this case, the material that Rogers has is a PTFE matrix. So it'll drill and plate just like a standard PTFE material. If you're familiar with like our Duroid materials, RT Duroid 6000, our Magneto-Dielectric material will behave a lot like that.
What Magneto-Dielectric materials does Rogers offer, and is there anything new coming out in the near future?
So we currently have one product. It's called Magtrex 555. It's a permeability of 6, a permittivity of 6.5 in plane, and it's low loss up into about 500 megahertz. We view this as kind of a new platform for the company. So we're constantly researching higher operating frequency materials, and higher permeability materials for lower frequencies. So we have one product now, and there'll be more products coming out in the future.
What is the effective permittivity that you get when you use Magtrex with the conventional dielectric materials?
It'll be dominated by so if you look at the hybrid use case, you need to understand the direction of your electric field. But let's say that in a patch, you're building a patch antenna structure. Your electric field will be mostly in the z-axis. And so it'll be dominated by basically a series mix rule between the dielectric constant of the second material and the dielectric constant of the magnetodielectric material, which basically says, let's say I've got a mu of permittivity of 5 in the z direction, and I take a material that has a dielectric constant of 2. And my rough volume fraction is I have 10% dielectric constant of 2 and 90% dielectric constant of 5. I'll get a dielectric constant that's somewhere around 3. And you can almost go back to like your Physics 1 textbook, or where you look at that capacitor example where you do a capacitor with air in series with a high dielectric constant material, and use those equations to calculate out the effective permittivity in that case.
Can you explain how you get this material through, is it through material synthesis or another option?
It's material synthesis, so it's not based on any sort of a structure that's patterned onto the material. You take a filler, ceramic filler that has one set of magnetic properties, and you blend it into a polymer system that has a set of electric properties, and your magnetic permeability will be 1 in the polymer. And then you control the volume fraction of the two materials relative to one another to give you a permeability over a frequency range.
Does Rogers supply free samples to universities or research organizations?
At this point for Magtrex, we're not offering free samples to universities. We're in a low rate initial production on the material, so we're kind of we're making sure that the material goes to places that there's a commercial use for it. Longer term, we may add this to our university sample program, but it's not in our university sample program currently.
How does the weight of the material compare to conventional PCBs or ceramic-loaded substrates?
So compared to a conventional ceramic-loaded substrate, this is a little bit higher in density. Something like a duroid material is going to have a specific gravity of around 2, so 2 grams per cubic centimeter. These magnetodielectric materials that we produce are in the 3.5 grams per cubic centimeter range. If you're looking at some of the ceramics that have been used in research, you're in the 5 grams per cubic centimeter range. And if you look at ferromagnetic metals, you're in the 7 grams per cubic centimeter range.
Next question, what family of ferrite is used with this type of material? Garnet, spinel, hexaferrite, etc.
Without getting into too much detail on that, because that's part of our research, it's a hexaferrite.
Okay, and then next question, is there a reason that the Magneto material is only available in the few hundred megahertz range? Are you planning on higher frequencies?
We are planning on higher frequencies. The reason it's only available in the few hundred megahertz range is physics of these materials. You want to operate at a cutoff frequency. You want your material for low loss to be something like 1/5 of the cutoff frequency of the material. So from a 500 megahertz low loss frequency, my cutoff frequency needs to be at about 2.5 gigahertz. Different families of materials will have a different intrinsic product, but generally you're looking at an intrinsic product that's in the tens of gigahertz. So if I want my material to operate at low loss up to 500 megahertz, that kind of sets the ceiling for what my permeability will be. And then if I want to go to a higher operating frequency, my permeability will drop. So we are working on next generation versions of the material that work to higher frequencies. But in the sub 500 megahertz range, that's really the frequency range at which your antennas are quite physically large. And so we see that there's a more substantial need for antenna miniaturization at lower frequencies where the antennas are fundamentally much bigger.
And so this will operate down into even the lower frequencies like kilohertz range too?
We've characterized it down to 1 megahertz. We haven't characterized it into the kilohertz range, but I see no reason that it wouldn't work in the kilohertz range. The trade-off would be in the lower frequency range, particularly kilohertz, you may be able to find other materials that maybe have a higher permeability. Or another way of saying that is if I were to design a material to work into the kilohertz range, I would start with a different magnetic ceramic that has a lower cutoff frequency and then would allow me to work to have a higher permeability.
Next question, how much power can the material handle?
It'll really depend on the antenna design, or another way of thinking of it is how concentrated the magnetic field is. The material, all magnetic materials will have a saturation magnetization above which, your permeability is effectively 1. So it's tough to answer without a specific example. What I can say anecdotally is we're working on this system to try to characterize permeability under biasing fields. And as part of that, we've learned just how hard it is to, in a physical structure, drive the material into a saturation region. So practically speaking, you're talking about you need to be above in the hundreds of watts to kilowatts range to really drive the material to saturation for most antenna designs.
Do you provide the frequency-dependent magnetic loss tangent data, and where can they download it?
We do provide it. It's not on our tech support hub yet, but it's something that we can send out via email in a tab-delimited file. So I would say contact your sales engineer, and they'll put you in contact with me to get the file.
Okay. How can you incorporate the frequency variation and anisotropy in simulators?
So the example that we've used the most is ANSYS HFSS. For that, what we typically will do is the model file starts with a tab-delimited table, and then there's a feature in ANSYS HFSS that allows you to open a tab-delimited file and basically manually import the values for every properties, right? So you'll have to independently import permeability, permittivity, dielectric, and magnetic loss. But it just imports directly in, and then it performs, I believe, a linear interpolation between those two frequency points. So if I'm giving you a value at 101 megahertz and 103 megahertz, and we're operating at 102 megahertz, it'll take a linear average between those two values.
Great. I think we've gotten to most of the questions here, and we'll respond to some of them offline. And I thank Carl for a great presentation, and thank you, Rogers, for sponsoring today's webinar. You can find out more about their products like this one and others at their website and their tech hub. This webinar has been recorded and will be available to watch in about an hour from now. You will find it in the events section of the Microwave Journal website. If your colleagues would benefit from watching it, please pass it along. And we thank everybody for joining us today.